So thanks everyone else for joining. This is our implementation week slash implementation week. And well, for the most part, in this monthly development cycle, we're just trying to apply some of the algorithms that we already implemented and try to apply them to challenging domains such as Atari and Mujuku. And we try to tune the performance so that we can have these files that are extremely simple to understand, yet still reproduce the state-of-the-art results. So I spent a lot of time trying to reproduce PPO because it's very related to my research with applying deep reinforcement learning algorithms to real-time strategy games. That's why I spent a lot of time on it. And as a result, I wrote a blog post explaining essentially a bunch of findings, a lot of details regarding the PPO implementation. And for those of you, I'm pretty sure everyone has already, well, the motivation behind this project was originally because we read the paper by Inkstorm, Ilias et al. So you can find a paper, but it's basically saying implementation matters for PPO and PRPO. Sorry, just for PPO. And they're saying there's a lot of optimization, code-level optimizations that are not necessarily mentioned in the paper that actually matters for the performance of PPO. And in particular, they list out 9 code-level optimizations. But when you actually implement, there's actually a lot more details than just these. So that's why I decided to sort of compile this blog post in a way to serve as a checklist. If you're implementing your PPO and it's not working for Atari or Majuko, then by reading this blog post, you can see maybe some of the details that you have missed, and it may help you to understand. When you're doing experiments, you might understand the working mechanism of some of these details and how they would impact performance. Just to kind of show you as an example, I sort of rename the files to different things. So previously we had PPO to continuous action.py to denote the PPO implementation that is augmented with all of the code level optimizations. However, I decided to rename PPO to continuous action.py to just PPO continuous action.py, and rename the original PPO continuous action.py to PPO simple continuous action.py to sort of denote that this is a naive implementation that does not work in general. And just to show you sort of what the PPO simple continuous action.py would look like, it looks like this. Sort of very simple, about 200 lines. And this is what I would consider what people would normally implement if they just read a bunch of reference implementations and try to apply the PPO into continuous action space. After a bunch of effort, actually, this is probably something they can implement. But as a matter of fact, this is the correct implementation from OpenAI baselines, which is significantly longer, about twice as long, with a lot of more moving parts. So I kept those 2 files just to sort of demonstrate how things can be so different, even though they're the same algorithm. And what is the complexity when you need to scale? What are some of the implementation details when you need to scale a simple to actually implement a published algorithm to achieve the reported results. But anyway, so this is a blog post that I wrote. There are 33 implementation details of proximal policy optimization algorithm. And by the way, if at any moment you have any questions, feel free to jump in and just stop me, and I would be happy to explain any details. So I guess for this presentation, I'll just kind of go over the blog post explaining some of the details, and but I guess before I do that, maybe it's more important. Maybe it's interesting to just show you. Well, maybe it's more direct for me to just show you the results. But essentially, we are able to reproduce PPO's implementation on a lot of Atari games. In Pawn, Breakout, the performance is very stable. The policy improvement is It's very stable. You don't see a lot of jumps as I see in some of the DQN or C51, at least in my implementation. And on Moduco, we're also able to reproduce the same results. And Hapchata, we achieve about 1,500 scores, and I was a little skeptical because it seems a little low. But then I run OpenAI baselines again, and then it achieves 1,500 the same. So in a sense, I verified a lot of environments, and in general, I'm pretty sure, I'm very, very certain this is a complete reproduction of all of the PPO's implementation details. To just, oh, by the way, also the implementation, all of the data is available in weight and biases as always. I just sort them. I just presented the charted the episode reward associated with each run. Of course, you can go into each one of them, and then first of all, there is this video of the agents playing the game, but there is also this requirements.txt that you can find out all of the dependencies, and lastly, this is a code you can download, and it really should be the case that you can just reproduce it. There should be, sometimes it's missing for whatever reason, but oh, I see. Because wait, is it a case that only I can see the commands that was used to run? Let me make sure. So if I click on this and overview, oh, interesting. So this is something that only I can see. It appears. There might be something that I can do about that. But essentially, it should be the case that you just copy this command, and you should just be able to reproduce the results. In any case, let's get into the details. So the first detail is obviously the clips are a good objective. This is a core feature PPO. So please implement it. And that's the same thing with the generalized advantage estimation. That is also, well, PPO, the PPO paper just say you can use an advantage estimator, but in practice, even in the paper, they do mention that they use GAE. And also, there is this normalization of advantages. So after calculating the advantages based on GAE, the advantage vector is normalized by subtracting its mean divided by its standard deviation. And in particular, this normalization happens at the mini-batch level instead of at the whole batch level. So an interesting thing, which I'm pretty sure it's the case, is that one of the very popular implementation from of PPO, I Kositrovkov's implementation, I am pretty sure he normalizes the advantages at the whole batch level, which should, because the rollouts engine stores everything. So this advantages calculation do happen at the whole batch level, which is not the implementation of OpenAI baselines. So that's the third implementation details. So I think that's something that is easy to miss, actually. And then there's also this value function clipping. And by the way, I included a permanent link to each of the call level optimizations. So you can just click on them to see where they originated from. But this is the value value clipping that is done by OpenAI baselines. So it is kind of similar to the way how the objective is optimized. You do some clipping something all around an epsilon threshold, things like that. And there's also this add-in learning rate annealing. So for Atari, the learning rate is set to decay from 2.5 e minus 4 to 0 as a number of time steps against the agent trained increases. In Majorco, it decays from 3e minus 4 to 0. And then there's also the mini batch updates. So PPO implementation of OpenAI baselines uses mini batch update to compute a gradient and update a policy instead of using the whole batch as in OpenAI spin-up. So that is also another sort of a discrepancy between the PPO implementation for OpenAI baselines and that of other libraries. And there's also this global grading clipping to make sure the norm of the concatenated gradients of all parameters does not exceed zero point 0.5. And there is this orthogonal initialization of weights initialization. So in particular, it looks something like this. And if you read the code, it says initializer equals to ortho initializer. And then the bias is initialized according to the constant initializer, and then the bias is always initialized to 0. And however, for the weight initialization, they sometimes use different scale. So, for example, you can see the CNN initialization for Atari. As you can see, it uses a convolution layer using initialized scale equal to numpy square root of 2. And then you can see over here that they're initializing the weights using the numpy square root of 2. And the same thing happens with the Majorco. So essentially, all of the hidden layers are initialized using orthogonal initialization with bias with the gain or scaling equal to numpy equal to square root of 2. However, the weights of the policy layer is initialized with scale of 0.1, and the weights of the value output layer is initialized with a scale of 1. So this is something that you actually have to do a lot of digging. You have to just set up a lot of breakpoints to find out where these things are, but this is where it is. You create a probability distribution for the policy gradient methods to sample actions from, and as you can see, the initialized scale is 0.01 for the policy. However, for the value function, it is initialized with scale 1. So all of these things, they happen at about 3 or 4 or even 5 different files, and it's very difficult to keep track of them. You actually have to set up breakpoints to step into a lot of methods, and just overall, there's a lot of things needs to be done to find out where they are defined. By the way, it seems the orthogonal initialization of OpenAI baselines is different from that of PyTorch. So if you look at PyTorch initialization for the orthogonal, it does some diagonal, some sign, and that seems a little different from the implementation from OpenAI baselines, which uses SVD and normal, but I consider this to be a very low level details and should not have a significant impact on the agent performance. And the use of parallelized environment. So PPO uses parallelized environment to speed up execution. As I mentioned in the paper, it uses fixed length trajectory segments. But don't worry about this for now because I dedicated a whole section for that. So yeah, I think the use of such environment is actually underappreciated by most people as it kind of changes the underlying MDP somehow. I'll dedicate a whole section to discuss it in detail. And then lastly, the epsilon parameter of the atom optimizer. By default, this parameter is not in the list of configure hyperparameters of PPO. However, it's set to 1e minus 5, which is different from the default 1e minus 8 in PyTorch or TensorFlow. So let me correct that typo real quick. It's not. All right. So these are Mujuko related hyperparameters. And something that people often don't realize is when you call something like this, baselines.run, you say a Mujuko environment and say you set a number of time steps, it actually invoke this vec normalized wrapper to the environment. that changes how the environment functions. So the source code is over here, as always. The permalink to the OpenAI's implementation of this detail is always linked. And essentially, they do this sort of normalization of observation. They clip the normalized observation. They also do reward scaling, which is very interesting as it applies a certain discount-based scheme. So the rewards are divided through by the standard deviation of a rolling discounted sum of rewards. And that is very interesting. So you're almost doing the discounted rewards calculation already, and then when you train an agent, you're doing it again. So this is a very interesting optimization, in my opinion. And then there's also the way the standard deviation is parameterized. So this is for the continuous action space. So to generate a continuous action, you need to generate means and standard deviation, and then you use those two values to create a normal distribution from which you can draw an action. However, this is not exactly the implementation from OpenAI baselines. Instead, it generates this logit for it outputs a logarithm of standard deviation. In addition, this logarithm of standard deviation is said to be state independent and initialized to be 0. So what that means is if you open it up, what you'll find is that it creates mean and log of the standard deviation, and that is initialized with the 0 initializer. Right. Yes. So that is an additional interesting detail, and so quite anecdotal findings. So when I was implementing this thing, I believe, PPO simple continuous action.py, it turns out for me, the logarithm of the standard deviation seemed to be important. So that's that. But I don't know whether it's going to have similar effect if I do that now with the new implementation, which is, by the way, kind of addressed by the paper. This paper on what matters in on policy reinforcement learning, a large-scale empirical study. I think they kind of mentions if it matters if you set the standard deviation to be dependent on the state or not. And I think their conclusion is that it doesn't matter that much. And then there's also the use of hyperbolic tangent activation for the hidden layers. And also, interestingly, when you use it for the Mujiko domains, you're not sharing the hidden layers between the policy and the value function. Instead, you're creating a value function with the same architecture from scratch. Lastly, the handle of action clipping to a valid range and storage. So after a continuous action is sampled, such action could be invalid because it could exceed the valid range of continuous action in the environment. To avoid this, there's a wrapper that is added to clip the action into a valid range. However, the original unclipped action is stored as part of the episodic data. So in particular, when you use a hyperbolic tangent activation, it usually it squashes the actions into the valid range. So technically, this should not happen. But if your environment is different, let's say have a range between negative 0.5 to 0.5, and then even though your action will be clipped, the invalid action, the original unclipped action, will be stored as part of the episodic data. And for details regarding the Ataris, so there's basically a bunch of wrappers, and as it is done in the original.
Just a quick question.
Yeah, go ahead.
If they store the unclipped actions, what do they do with it?
Sorry, what was the question?
In case the action is not squashed to fit the range of valid action of the environment.
Mm-hmm.
You said they still store the unclipped action in
Yes.
whatever store.
So
They do anything with it.
they don't do it, right? So if you look at its wrapper, so the actions, the environment is essentially wrapped with this clip action wrapper that clips the action to the valid range. So there's no way for the if you look at how an action is sampled, an action is just being sampled, and then that's it, and then it's being stored as part of the episodic data. So there's no way for the agent over here to have access to the environment, that wrapper. That there's, I don't think they. I'm pretty sure they don't get the clipped action to store over here.
Okay.
Yeah.
Makes sense.
Yeah, there's no code that does that. I'm pretty sure. Then there's some Atari specific implementation details. Essentially, a lot of wrappers are used. The use of no-op reset env. So samples the initial states by taking random number of no-ops on reset. And then usually this is set to have a maximum of 30 no-op action. And then there's also this fire reset. So if an environment needs to be started by taking a fire action, it does that automatically. There's also this episodic life env that makes end of life equal to the end of episode, but only resets on true game over. And there's also this max and skip env, so repeats actions for 4 frames, some of the rewards achieved in those 4 frames, and returns a max pulled observation. And there's also this wrap frame, which transformed the images into 84 by 84. And there's also this frame stack that stack the 4 of these 84 and to 84 images. And you also need, and there's also the clip reward env that clips the reward to -1 or 1 or 0. So in a case of breakout, for example, it's possible that for each of the frames in the frame stack, which are 4 frame stacks, you can get 4 +4 rewards. And essentially what this clip reward env does is to clip that so that your reward is always +1 or -1. And for my experiments, I find this clip reward env to be actually really important. If you don't set it, then the agent actually overlearns, and then you see the learning becomes significantly more unstable. And that is actually the same thing with C51 as well. Using this wrapper, the agent is able to consistently reach about 400 reward. While if if the reward is not clipped, then the agent will usually achieve something like 350 or 330. But obviously, the 351 is not very well tuned, as it is shown over here. It's not really achieving the reported results on the paper, but it's kind of difficult to tune. And C51 actually takes quite a long time to run. As it is shown over here, it takes about 1 day, 3 hours. So very expensive, very long, takes a long time to run. And also, the input data has a range from 0 to 255, but it's usually divided by 255 to fit the range of 0 to 1. So in particular, when you build the neural network from OpenAI baselines, it transformed the images by divided by 255. My initial experiments, which at this point might not be true anymore, but I find the scaling to be extremely important. Without it, the first policy updates results in the KL divergence explode, likely due to how the policy are initialized. So if you remember the way policy are initialized, they're in a sense have very small weights, and when your observation is so huge, I don't know. So this is a very intuitive explanation, but I think it's possible for it to just blow things up and results in degenerate updates. And then there's also the use of ReLU activations, and And also they share the hidden layers for the policy and the value functions. I don't think it makes actually in the paper reported over here, at least for Mujuko, they find sharing the layers between the policy and value function is actually slightly undesirable than sorry, the paper's conclusion was that you should initialize the policy and value function separately. And there's some auxiliary implementation details. So for example, the clip range annealing that is not actually being used. It is implemented in Open Baselines library, but it's not being used for both Mujuko and Atari experiments. They also use MPI to do parallelize a gradient update, but I think this is handled automatically by PyTorch. So there shouldn't be anything we have to worry about that. And there's also the early stopping optimization. This is actually not an implementation detail of OpenAI baselines, but rather an implementation detail in OpenAI spinning up. Their early stopping optimizations measures the mean KL divergence between the target and current policy at PPO and stops the policy updates of the current epoch if the mean KL divergence exceeds some preset threshold. This feature is implemented and can be toggled by using KLE stop. I just kept finding these typos. All right. Right. So, does anyone have any questions at this point?
No questions.
Okay. All right. So let's go into the detail of parallelized environment because I think it's something that most people don't really understand its significance and how it works. So in a paper, this is a screenshot of the paper this is a screenshot of the paper, and it says PPO algorithm that uses fixed length trajectory segments is shown below. Each iteration, each of the n parallel actors collect t time steps of data. Then we construct surrogate loss on these n times t time steps of data, then optimize with minimatch SGD. So I think this is a very crude oversimplification of what is being happening. So to really understand what the parallelized environment mean, it's important to understand how a game could terminate. So in particular, a game don't always terminate at t time steps, right? It could go on for, I don't know, t plus 5 or t minus 1. Usually the game has variable number of time step that you could run. So anyway, the first type of termination is a true termination, where the episode of the game really terminates. As an example, the true termination of the breakout game in Atari 2600 comes when you lose all of your lives. And the second type is time limit termination. To avoid the episode of the game to go on indefinitely, the episode of the game is set to finish with a maximum of n time steps. So to illustrate, let's consider a toy example called TestM, and that always outputs its observation as its current time step from t equal to 0 and always truly terminates at t equal to 10. So what that means is that if you run the episode, this is the observation in episode 0. At time step 0, you get observation 0. At time step 1, you get observation 1, etc., until observation 10. So this is a true termination. So the horizon is 11 because it goes from 0 to 10. However, in real games, at this age could get arbitrarily large. So imagine if you just open a game of, I don't know, Overwatch, or probably not Overwatch, but imagine if you open a game of StarCraft 2 or Dota 2, and then you do something, maybe almost winning the game, but you just never do anything else other than that, and you just go eat a lunch or go eat dinner, and then the game could still be running. So in theory, this true termination condition could never come if you just let the game to run forever without ever triggering the termination condition, which is very bad because in order to let the agents to be trained, in order to collect episode data, we actually need the environment to finish. We need to collect finite number of data. And to avoid this situation, usually people put this time limit wrapper to say, okay, no matter if the true termination condition comes, we'll just terminate it once you exceed certain time limit threshold. So how that's being done is essentially when you register an environment, you say max episode steps equal to 8. So as an example, carpal has the carpal V0 has the max episode steps equal to 200. And again, we run for 2 episodes, and as you can see, the environment always terminate at t equal to 8, and you see the terminal observation is array 8. So that's a time limit termination. However, as I mentioned, even if you added the time limit, sometimes the time limit could be very huge. So in a game of Dota 2 that lasts for millions of time steps, actually, by reading the paper, I realized it's more like hundreds of thousands of time steps. But how do we handle all these observations without blowing out the memory? So if you look at how the PPO continuous action is the simple continuous action is doing, it's creating a NumPy array of the episode length. So if you the default episode length of Atari is actually 400,000, and then can you imagine creating multiple of 400,000 length array? If you have a regular computer, NumPy will probably just tell you unable to allocate the memory. So to alleviate this problem, this is where the vectorized env come in, or the parallelized environment. It reduces the episodic observation to fixed length trajectory segments, which introduces the third type of episodic termination, which I call early termination induced by fixed trajectory. Here is an example. I import the vector env from stable baselines. I think this is a reasonable dependency because it is very well documented and its behavior is could be highly expected, and it's not likely to be changed, like it is the case with many DRL unlike the case with many DRL libraries. So I think this is okay to have this dependency. So if you look at it, then the episode, or in this case, it's actually using trajectory as the episode. The trajectory is very interesting, right? The first trajectory for the episode is 0, 1, 2, 3, 4. And the second trajectory is 5, 6, 7, 0, 1. And then the third one is 2, 3, 4, 5, 6. So just by looking at this, what do you guys think? Any particular observation?
It's a continuation of the previous trajectory.
Sorry, say that again.
I think it's a continuation of trajectory 1 is continuation of trajectory 0.
Yes, exactly. So the trajectory 1 essentially has some part of the real time limited episode 1 as part of his as part of his trajectory. So here is a list of observation we offer. So the initial observation of the trajectory is no longer 0. So trajectory 1, the initial observation is 5. Trajectory 2, the initial observation is 2. So, which means the initial state distribution of the trajectory is no longer the same as the original MDP. Instead, it kind of relies on the Markov assumption that your state should be representative of all of your historical states. And it assumes your agent is able to learn to execute certain actions if I just give you any states in a game. So that's sort of the first observation. The second observation is a time-limited episode of the game is broken into pieces presented in different trajectories, as it is shown over here. And lastly, the terminal observation, the time limit terminal observation, rate 8 is not present in any trajectory. So the benefit is obvious because if you want to train a game, let's say Dota 2, then you can just do this and you set the fixed length, the length of this trajectory segments to be something like 1,000 or 2,000 or 5,000. It doesn't matter because as long as you use this kind of ways to update the episode, then you can handle arbitrarily long horizon, such as 1 million. That's not a problem because you break the episodic observation into these trajectories as the episodes for the agent to optimize. By carefully storing variable stuns and use value bootstrapping, it is still possible to calculate advantages and return to update agents, as it is done here, where essentially the agent bootstrap the values given the last states. So in effect, it's saying I look at this state, I look at this state, I look at this state, and bootstrap a value based on that to say, oh, what would happen if I had let this environment to continue to simulate? So by using these techniques, it is possible to still calculate advantages and returns to updated agents. However, notice OpenAI baselines only bootstrap values if the trajectory is terminated due to early termination. So it happens over here, right? 416, it happens over here. However, it does not bootstrap values if the time limit termination happens. So in particular, time limit termination happens over here, right? Because at 7, you reach the terminal observation time. You reach the time limit terminal observation of 8, but then it's cut off. But then there's no value bootstrap based on the terminal observation of 8, even though the game really terminates at something like 10. Yeah, so those are essentially some observations. And if you look at Ikostrakov's code.
Kostrikov. Okay.
Do you know how to pronounce it?
Kostrikov.
Kostrikov. Okay.
Yeah, it's Russian.
Did you just guess, or is that actually how it is being pronounced?
Yes, it's actually Kostrikov in Russian. But...
Oh, okay. Kostrikov. Okay, that's better. Thanks. In Kostrikov's code, as you can see over here, it has this flag called use proper time limit. And I think that's what he's trying to address over here. Because OpenAI baselines only bootstrap values if the trajectory is terminated due to early termination, but does not provide value bootstrap if the time limit termination happens. However, over here, it's also not doing value bootstrapping on time limit termination. I'm not exactly sure what he's trying to do over here, honestly. But it seems to be that's something that Kostrikov is trying to address. But I'm not sure, because in order to provide bootstrap for the time limit termination, which in a sense, if you think about it intuitively, this is what should happen. If your environment terminates due to the time limit, then you should bootstrap the values on the time limit based on the terminal observation of 8. But that is apparently not the case with Kostrikov's implementation. Anyway, so the results, as I already presented in the beginning of this presentation, it's all very, very good. pretty much, except for some environment. Well, obviously it's not the best, but it's interesting to inspect into some environments, such as Hapchata V2. It reaches around 1500 scores, but then look at what it learns. Which is kind of interesting because it learns to walk with its head rather than using its feet. Actually, have cheetah, yeah.
Welcome to the future.
Yeah. So for me, that is very interesting. And I thought I had a bug originally. I was thinking, oh man, did I miss another detail? And maybe I wasn't reproducing it correctly. And then I rerun OpenAI Baseline's implementation of PPO2 with the same parameters. And then it reaches 1500 scores exactly. So in all of the environments I tested, this is a really good reproduction, and it matches all of the scores produced by OpenAI baselines. Excuse me. Yeah, go ahead.
Is there a reason why the terminal observation is not present in any trajectory when you do early stopping?
That just seems to be a design choice made by OpenAI baselines. It's just saying if you're hitting time limit, good enough. We consider this as true termination.
Okay.
Yeah, which is something that may or may not be true, and that's why making the source code as easy to hack, as easy to interact as possible is important, because you can just try it out. You can use, probably not shown over here, but in the info section, when you step the environment, you can actually get the terminal observations. So technically, you can bootstrap a value based on the terminal observation, based on time limit terminal observation, and then you adjust your calculation accordingly. Then it is possible to do that, and it wouldn't be too much more complicated. But it just kind of highlights how easy it would be to do something like that if you use a single file based implementation. Because using OpenAI baselines, you have to know exactly where to modify, and debugging is very difficult.
Yeah.
But anyway, so this is very interesting, right? So I say this highlights why you need the videos of the agents playing the game to develop better understanding of the agent behavior. And this is the case with the empirical investigation shown over here. In fact, if you read the paper, all of them have cheetah environments. So for example, when using the default setting, it reaches 1500. So that is the exact result that we get. And actually, in all of the right, yeah. So sorry, that's basically my point. So it reaches about 1500 reward, and this is something that you'll never be able to get if you're just looking at 1500. You're probably thinking, "Oh, that's good," but then you look at this. In a way, it's really. In a way, obviously, the agent learns something and it's able to achieve our desired task, but also in a way, you really shouldn't be saying it learns good policy. So that's for that. And we also have a fun visualization of the action probability distribution, which is done by this wrapper. So the videos of the agent playing game are recorded through the gem monitor wrapper, which essentially records the video based on the image numpy array produced by this method. And by overriding this method, we can actually visualize the action probability distribution. So what I did is essentially override the render method and hijacks. Basically, I inserted a visualization of the action probability distribution. And this is what it looks like. This, again, also gives you so much insight on the agent's performance, as we will see in a minute. But essentially, it performs pretty good. By the way, the first action over here, 0, is no op, and second is fire, third is right, going right, and the last one is going left. But what's interesting is when you get into later stages of the episode, the agent doesn't really do anything. It just does the same thing over and over again, always hitting the brick over here, and never do anything else. And in order for the agent to actually do anything else, in a way, I almost actually have to hit the when the epsilon greedy policy kicks in to do exploration. That's when this happens. The agent actually hits the brick to a different location. Right. So yeah, again, why this highlights why it is important to inspect the agent's behavior. Very interesting. Another interesting thing, which I did not include in this blog post, is look at its probability distribution. It fluctuates very well. However, if you compare that with the return visualization of, let's say, C51, it looks completely different. So here is an example. So if you look at its return, the Q values for the actions, they actually don't fluctuate as much as the probabilities will fluctuate. The values are generally more stable, but then sometimes you see a peak in a particular action, which is kind of interesting. So in particular, if you just convert these Q values into probability distribution directly, you'll find 25, 25, 25. But that will not be the case for whatever is over here. As you can see, one is always significantly better, significantly more preferable than the other. And yeah, some notes on reproduction of all of the results. It's published over here. If you want to reproduce everything, just run these commands. I would not recommend running all of them at once, but yeah. What else? Yeah, lastly, I did a little critiques, a euphemism for trash talk. But essentially, I just say a lot of existing DRL libraries are there's some problems with them. There's some design choices that I don't really enjoy. They're difficult to understand, as it is a case with PPO. It's a lot of the details are actually distributed at all kinds of files all over the place. And the inspection of the baseline's PPO directory is simply not enough. And it's also difficult to inspect and debug. As I was trying to figure out where those things are, I have to set up breakpoints. And if I want to print out something, that is very difficult. I have to use a breakpoint, and every time I have to do that. This makes iterations very slow. And also, it's difficult to customize and research. Imagine, as an example, how much effort would it take to include a technique called action masking, invalid action masking. So this is how much effort it would include. In comparison, if you use single filed implementation, this is how much effort it'll include. So yeah, it just kind of highlights when you deal with this kind of sort of cathedral types of a DRL library, it becomes harder and harder to incorporate new features. And additionally, I put this argument that says they usually have awkward modularity with bloated functional arguments. And the example with this invalid action pull request is one example. It even includes this invalid action mask for DQN somewhere. But DQN cannot use invalid action mask. So as it is shown over here, it acts based on that. However, it really should not be used. Policies, let me see. Does it actually use it? Oh, never mind. It actually uses it. But I have never seen invalid action masking be used with Oh, sorry, it doesn't implement it. It just put it over there. See, the step, it just says raise not implemented error, right? Let me see. Wait, how can I inspect this file? View file, maybe. Yeah, so as you can see, a lot of these step methods are actually not implemented for some reason, because there's no one knows how to use invalid action mask for DQN. I'm pretty sure, but I would rather not to thoroughly examine it. But this for me shows a problem. You can't just add another thing to the functional argument every time you have a new feature. Eventually, this step method is gonna have like, I don't know, 5. Sorry, it already has 5, but rather maybe you would have 7 or 10 or I don't know 20. And as a beginner, if you're just reading on DQN and you look at this action mask, you wonder what is that action mask, and it's not referenced in the paper. It becomes very difficult to understand. And similarly, if you're not using prioritized experience buffer, a replay buffer, then you might be wondering, why is there a waits argument in a replay buffer in a DQN method? Similarly, if you're not using recurrent network, this actually confused me significantly. Let me see if I can find it. But over here, you have this MB states, and then you have this mini batch observation, mini batch states. And for me, I was wondering, what does this mini batch states do? And it turns out it's for recurrent network. And this is another thing. Basically, whenever you want to add new features, your functional arguments or your code becomes more bloated, because you try to incorporate these features while still handling the simplest cases possible. As a result, the simplest case, your code could not be simple anymore because you want to handle all these features. But in general, I think it's very difficult to design good modularity with DRL algorithms, because the DRL algorithms are always evolving. It's very hard to design modularity that captures this rapidly changing structures. And when that happens, it's very easy for your early design choices to become obsolete. And you have to either do a major refactoring, which costs significant effort and testing. And secondly, you have to awkwardly, if you decide to not do a major refactoring, you have to awkwardly fit new features into existing code base, as it is shown in the pull request for the invalid action masking, which again is also not preferable because it makes the code harder to understand. And I just say CleanRL address the first issues by putting all relevant code in a single file, so it's easy to understand. And secondly, this is how I debug and develop, right? So for example, I Control C and I can see the agent's weight in bias. Sometimes this is helpful if I want to have some sort of reproducibility between different files. I'll try to seed everything and see if the agents are initialized with the exact same weights. And also, you can just print out things like that. And in terms of, and this only shows how to calculate the advantages and returns using GAE. However, what if I want to calculate the returns regularly? Well, the thing is, with Spider or any sort of interactive IDE, you can do that in the interpreter, in the interactive shell. And then you can debug it on the fly. And then once you have satisfactory results, you just sort of paste it back. And that's it. That's sort of the development flow. It's very seamless. It's very easy compared to setting up breakpoints and always running the file from scratch, as it will be the case for many DRL libraries. And lastly, there are some research-friendly features: seeding of everything, cloud experiment management, video recording, integration with AWS Batch. Here's a screenshot of us running thousands of experiments on AWS Batch. A long-term goal is to create this OpenRL benchmark that transform this static benchmark image into this interactive thing that you can check the videos of the agents playing the game. You can check the videos of the agents playing the games at different stages of the training. You can check all of the hyperparameters. You can check all of the metrics, all of the system metrics, including CPU utilization. You can check all of the files, including this requirement.txt. You can see the source code. And then you can see the commands that allows you to reproduce it exactly right over there. So I see its great potential in not only bringing the transparency of RL implementation to a whole new level, but also accelerating research because reproduction of these algorithms will become trivially easy and readily accessible. And lastly, some concluding remarks. So yeah, that's basically what I have. Any questions or comments?
No, that's a real big work. I think that's really good.
Thanks, Niju.
Yeah, really dense, lots of information, definitely.
Yeah. Well, what would you guys say is the most confusing part for you, maybe? Well, I'll be surprised if.
I would say it's the
Go ahead.
part concerning the early termination, strapping, and the VAC-env kind of. Well, I think it was early termination, time limit, and the real termination. And regarding that, actually, I have quite a comment, which is that even if we use, for example, the early termination of the VAC-env, right? The initial distribution of the initial state distribution still does not change as long as we use bootstrapping. So it's like a really detail. But
why would you think the initial state distribution will not change?
If there is no bootstrapping, it will not change.
But the thing is,
wait. If there is bootstrapping, because with bootstrapping, the agent gets the illusion that even if it was early stopped, well, it's not the real end. So yes, exactly at that part, even in the trajectory 0, even if the final state is 4, right? If we do not bootstrap, so next episode array 5,
So I'll offer one observation, right? So initial state distribution does not happen at the end. It has nothing to do with what happens when you terminate the episode, terminates the trajectory, and do value stripping. It has nothing to do with that. It has to do with how how your trajectory begins. And in this case, for example, the second trajectory, it starts with observation 5. So from the PPO standpoint, it doesn't know it's just a trajectory. It perceives as an MDP or observation, and it sees the first observation is 5. Does that make sense? And all of the advantages calculations are not reused from the previous calculation. It's only the states that are reused.
The way to.
Yeah, think about it.
It's a little bit more complicated than that. What is an initial state? How does the agent know if the state is initial? It's when the Q value function. I guess PPO we use.
I don't think the agent really. I don't think the agent really knows what the initial state is. Like this is more of a, in a way, more technical than actually matters, right? Because the initial state distribution is sort of a concept in MDPs. You're just saying your game always starts with the initial distribution of states. Well, here I initialize the game to always have the initial state distribution to be 0. However, when the agent is being trained,